Okay, we continue on concept 24 with volume. If we know slices, that's the easiest. If we have to figure out our own, there's a few other things we can do. They either have discs, which are solid, like think about if a coin used. I don't think many of you have compact discs anymore. Records are coming back in. That's not really a disc because there's a hole in the middle. It's more of a washer. Uh, so you either need to think about is the shape solid or hollow. It depends on what you're rotating. So if you had a curve here and you rotated this around the x-axis, it would be solid. But if you took that same curve and had another curve with it and you said, I want to rotate this piece, now it's going to be hollow. There's going to be an inside piece that's taken out. And so if you want a visual of it, you draw the reflection and then connect it with curves. And then you have to think about taking a big radius and subtracting a smaller radius. Big R squared minus little r squared. Don't forget the pi. All we're doing is taking circles. When you turn and look at it, you have a circle. And so you either have a circle that's solid, where we're finding the radius, so the area is pi r squared, or you have circles that are hollow, and we need to know if we take the big R and take away the little r, that gives us our part that's left over. And again, remember that integrals are accumulating functions. So in this case, we're accumulating circles or washers. In the other cases, there were slices of squares. And the width, they're really cylinders because the width is dx. It's super thin. Just some different example ones. I'll keep working through those, so you can have something to check with. Okay, position, velocity, acceleration. We started with this. We got back to it. There's a derivative application. There's an integral application. My abbreviated version is you have position, velocity, which is position divided by time, and acceleration, which is velocity divided by time, which means it's position divided by time divided by time. And to go down the ladder, you take the derivative. I'll just even write derivative. And to move back up, you're going to integrate. So think about where you are at, which direction you need to move. And then there are a couple of terms that go along with it. Displacement and position. Those are a couple different words. And sometimes they get mixed up together. And total distance. So we can use an integral like this one. This is the graph of the velocity. So the area represents the integral. And remember, if it's above, it's a positive. If it's below, it's negative. This means all of this area would be the change that is accumulated from during that time in the positive direction. And then this would be the change that is accumulated in the negative direction. If you wanted to find how far they drove, you would make this an absolute value and add them together. If you wanted to find out where you were at, you would add these two together and then configure in where you started. So it just depends on what the question's asking. But again, working your way down, working your way up. I can't emphasize enough not to forget to include initial position if it is given, if it's relative to the problem. You can do all your good work with your integrals. Let's say you find out this is a net of negative 20, and you say, well, he went 20, blah, blah, blah. Well, that doesn't matter if you don't take into account where you started. So we're sitting at this place. We drive here, we drive here, we drive here, we drive here. Well, don't go through all the work of finding out where you drove and then never figure out the initial position. Okay. Related rates. fairly complicated concept if you have to write the equation. If they don't give you an equation, if they do give you an equation, it's not a complicated concept. It's an application of implicit differentiation. We're just taking the derivative with respect to time. So let's just pretend we had a formula for area that somebody gave us, and when we take the derivative here, we take it with respect to time, and you just take the normal derivative. Derivative of h is 1, but we need a dh dt. Now let's just even pretend that wasn't h, so if that's r for some reason. And the derivative here would be 4r dr dt. So you end up with 1, 2, 3, 4, possibly if there was another h there, missing values. You're going to have 3. They might have to give you 3. Some of them are easier to find than others. Some of them you can plug back into one of the original formulas and solve. Sometimes we make like little similar triangles here. It just depends on the question. But anytime they're asking you to compare multiple variables in the same equation with as far as a change, if you see a rate of change more than once, you know that you're going to have to do implicit differentiation. Now, in a problem like this, you might be able to write the radius in terms of the height. Like right here, you see the radius of the big shape is 5 and the height is 10. So the radius to height is a 2-to-1 ratio. So you might be able to rewrite the radius as half of the height. And then you eliminate a variable, which eliminates you trying to figure out dr dt. Last concept on this paper, adding and removal problems. And essentially these are applications of integrals and taking away of integrals. How many gallons of heating are pumped into the tank? Again, I have worked out several of these problems. I would suggest you look at them, or look at some. If you don't like my work, look at somebody else's. There's tons of these accumulating problems. The key is, if you know that this is a removal and this is an entry, I think that's what this one pumped into. So the amount pumped in minus the amount removed is how much you have. Okay, and so you in your tank. Okay, so at any given time, you also have to figure out that what you started with. So like in this one, it has 125 gallons plus all the crap going in, and oil in this case, minus all the crap going out, and that'll tell you where you're at. You can put that in one integral or two integrals, depends on how the information is given. Again, this is just like that last one with the graph. Don't forget integrals as accumulators. You can watch the 5 videos if you want. This is how much you start with plus the change based on the total derivative. The integral of the rate is the total change that happened. And then you know where you end up with. Okay, so that's my fast summary of these 27 concepts. There are some other ones, things to memorize, that sort of thing. This was just a paper that I found. And it gets you a good start. And then I would encourage you to go to the internet. There's a guy that does like the all in AP calculus in 20 minutes video. It's kind of funny, but it's a good fast one. I wouldn't watch it the night before. You'll just get stressed out. But I'll work back through some of these and get you an answer key, or you can come see me as you work through them. And we'll talk some more as we get closer to the test.